Okay, so good evening, good afternoon, good morning, everyone. Welcome to part 3 of the measure phase of the Lean Six Sigma Yellow Belt training. By the way, how is my audio? Can you hear me?
Yes, sir. Loud and
Awesome. Okay, let's continue. So, just a recap, we are following the DMAIC methodology as we cover the Yellow Belt tools for Lean Six Sigma. We have finished the define phase and we are now in measure phase. We have covered 2 parts of measure, and this session we will cover the 3rd part of measure phase. In measure phase, this is where we quantify the pain points that we are dealing with in our project. So the measure module, the measure phase, is composed of 3 parts. We have covered statistics background in part 1. We have covered graphical tools in part 2. And now this is part 3, and we will talk about process capability. And the way we discuss process capability will be dependent on the type of data that we will have, whether it's discrete data or continuous data. But before we proceed further, I'm going to flash you a slide here which asks a question. Which river is better? Now, if you are posed with that question, that could be a bit quite tough to answer. When you say, what do you mean? So I'm showing here 2 photographs. Okay. Which do you think, which river is better? Any thoughts you can put in your in the chat box for your any comments? The one on the left or the one on the right? Okay, anyone? Well, let's see from the chat box. Okay, so someone said we need more data. Someone said the right one because of the color. Actually, here the answer to this one is a bit. There's no right or wrong answer because the question is a bit ambiguous. But if the question were which river is longer, then this would be easier to answer. The one on the left side is the Nile River, and the one on the right side is the Amazon River. So if the question is which river is longer, then we know that the answer is the one on the left, the Nile River. Next question. Okay, this one's a bit controversial. Which player is better? The one on the left or the one on the right? And you can answer your questions in the chat box. So we have someone answering Stephen Curry, not being sip. Okay, so again, this question is also ambiguous because you can ask the context, what do you mean by better? So if our reference is the average number of points in the game, then the one that's a better score would be LeBron James. But if you're talking about the accuracy of shooting point accuracy from the 3-point line, then the answer here would be Stephen Curry. So again, the answer to this question will be it depends, because on what context do you want to answer that question? Next one, which country is better? Okay, the one on the left is Finland and the one on the right is, of course, Philippines. What do you think is the answer? Yeah, you can answer in the chat box. Okay, great. So someone answered with the context. If we are talking about happiness index, it would definitely be Finland. Okay, they rank, I think, one of the highest, if not the highest country in terms of the happiness index. If you're talking about the per capita income, it's definitely Finland. So this question is controversial as well because you need to put some context. So I was a bit curious. I asked ChatGPT to this question, which country is better, and then ChatGPT was quite safe when it responded to the question. But in terms of the examples that it was given, it was more on Finland. So I asked ChatGPT, so in which aspects is Philippines better? So I think in the aspect of probably the temperature or the climate, then we would be much better in Finland. But it seems that in all other aspects, Finland is scoring higher. Okay. What about this one? Which candidate is better? So I know that the Philippines is quite a big fan of basketball and pageants. So so someone answered Pia. So again, the answer is depends on the context. But if you talk about the crown and the way that the judges have responded to this one, then we would say that in that context, the one on the right is the better candidate. Okay. And finally, oops, I pressed the wrong button. This one, which process is better? The one delivering the pizza, or the one fixing the car? So here you might be wondering, can you compare actually two different processes? Okay. So in this case, we need to come up with a measure that somehow is able to measure a process. And actually, there is a way that we can determine whether one process is better than the other. You can actually come up with a term or a concept that somehow would compare apples to apples. And now you can actually have a way of determining whether your process is actually better than someone else's process in the context of what we call now the process capability. So we would know whether one process is better than the other process in the concept of process capability. And that's the topic of this session. So what is process capability? So process capability talks about just the reproducibility of your process output, okay? And how it is performing with regard to the specifications. It tells you of how uniform your process is. So your process has a good process capability if it is uniform, it is consistent, it is able to reproduce the same output that it had before, and if it is producing it according to the specifications required by your client. You can talk about the capability of your process in terms of these are the total outputs of your process, and how much of this are within product specifications. So it could be in terms of the percentage, right? So let's say if you produce 100 products, how many of these products or how much percentage of these products are actually within the specification limits of your customer. And you can measure that in terms of percentage, or if you have a lot of output, you can measure it in terms of parts per million or even parts per billion. Okay, so process capability. But actually, process capability can be described in the way or the type of data that you are dealing with. Okay, so if you are dealing actually with discrete data, you can describe your process capability in terms of what we call DPU, or defects per unit, or defects per million opportunities. But if you're dealing with continuous data, you can describe your process in terms of a concept called CPK, or the sigma level. Okay, and we will be discussing how to compute for that in the succeeding slides. So before we will discuss discrete data, let's review. I think we've covered what is discrete data and what is continuous data in the previous sessions. So let's review. I'm giving here 5 examples, then you determine whether the data that is required here is discrete or continuous. So the first one, number of errors in a form, is that discrete or continuous? Yes, the answer here is it is discrete because you count the number of errors. So anything that is counted is considered discrete. Number 2, number of trains that are late. That is discrete. Okay, so you just count the number of trains and you consider, is this train or late or not? Then so you count it, so it's discrete. Number 3, average time to process an order. Okay, that is continuous. Okay, time is a continuous data. And number 4, price of an item, or the monetary value of an item. Yes, that is actually continuous. Money is there could be $1, $2, but there could be 1.5, 1.3. So cost is actually a continuous data. Speed of a car, okay, it is continuous. Speed of a car is continuous. Now, before I move to the next slide, notice number 2 and number 3. Okay, so in number 2, you're talking here of number of trains that are late. Late can be measured in terms of time. But in this case, since your data is about number of trains that are late, this is discrete data. But in the future, if you are dealing with a challenge about let's say timeliness, you may want to think whether you can convert your data in from discrete to continuous. So in this case, let's say your challenge is about the timeliness of train. You can actually capture it in terms of number of trains that are late, or you can actually measure it in terms of the travel time of the train. Okay, so now when you talk about travel time of the train, then now you have shifted the problem from dealing with discrete data to dealing with continuous data. So in the future, if you are handling a Yellow Belt Lean Six Sigma project and you have the opportunity to shift your focus from discrete data to continuous data, it's much better to work with continuous data because you can derive more information in it. Okay, so let's move on. In the concept of the discrete data, when you talk about the process capability, we need to identify what is considered as defect and defective. Okay, so if an item does not conform to the requirement on one or more characteristics, it is considered a defective. So a defective would refer to an item. A defect is a non-fulfillment of a characteristic. But if this concept confuses you, I think number 4 is probably the best reference. A defective will contain at least one defect. Okay, so a defective can have one or more defects. So an example of a defect: a wrong entry in a field, whereas a defective would be it's an HR form. An HR form can have many fields. So an HR form with at least one field that is missing would be considered as defective. A defect would be a missing topping. A defective would be a pizza order with wrong toppings. Okay, pizza order is one item. Okay, a defect could be a scratch on a phone, and a defective will be the phone itself that has a 5-inch long scratch. So a defective, which is the phone, can have 1, 2, or 3 or more scratches. So a defective can have one or more defects. So to further illustrate the concept of defect and defective, let's have an example. So in this example, let's say Glenn works in an HR department and one of his tasks is validating loan form submissions. So there are loan form submissions. And the loan form has 10 fields for information. Okay, let's say these fields would be, let's say, surname, first name, middle name, date of birth, sex, eligibility status, zip code, the type of loan, the loan amount, and the date of submission. And let's say Glenn reviewed 20 forms. So one form had missing info on loan amount, and another form had missing info on zip code and eligibility status. The question now is, how many defects did Glenn encounter? Okay, so the question is, how many defects did Glenn encounter? Can you answer in the question, in the chat box? Okay, someone answered 2, someone answered 3. The correct answer is actually 3. There are actually 3 defects. So one is on the loan amount, the other one is the zip code and the eligibility status. So all in all, they had 3 defects. And the next question is, how many defectives did Glenn encounter? How many defectives? So the answer is 2. Yes, there are 2 defectives. So because one defective is the form which has a missing info on the loan amount, and the other defective is the form with 2 defects, the zip code and the zip. Okay, so I think you know the concept now of distinguishing a defect from a defective. Now in discrete data, there are 2 common measurements. This is what's called the defect per unit and the defect per million opportunities. Okay, so the defect per unit is you just count the number of defects and the number of units. So in the previous example, we had 3 defects and the total units, 1 unit here is one HR form is considered as 1 unit. So there were 20 units, okay, and there were 3 defects, so that the DPU in that example was 15%. Another way of measuring process capability for discrete data is in what we call the DPMO, or the defect per million opportunities. Okay, so there's a new concept here called opportunities. So an opportunity is any opportunity where a defect can happen. Okay, so in the previous example, 1 unit there is the HR form, and there are 10 opportunities where an error or a defect can happen. So per unit, there were 10 opportunities. Okay, so the DPMO in that example was you count the number of defects. In that case, it is 3. You count the number of units and the number of opportunities. So the denominator will be there were 20 units and there were 10 opportunities. How do we interpret the 10? We say that there are 10 ways that a unit can have defects. Okay, and that's where the 10 comes in. So you multiply that and you multiplied it with 1 million. The answer here is the DPMO in the previous example is 15,000 DPMO. Okay, so which means that if you have 1 million opportunities, there will be 15,000 ways where you can encounter the defects. Okay, so those are the 2 measures of process capability if you're dealing with discrete data, the DPU and the DPMO. Okay, let's have an example. Okay, so a self-assessment questionnaire form has 30 fields. And let's say John went through 50 SAQ forms uploaded in a platform and he found 2 defective forms. Okay, so one SAQ form had 3 defects. They had the wrong site name, wrong number of workers, and a missing info on auditor. Another form had 1 defect, which is, let's say, the grading matrix. And the question now is, what is the DPU and what is the DPMO? Okay, if you can answer that with your calculator and put in the chat box, let's see if you get it. So what do you think is the DPU? Anyone? Can anyone hazard a guess? I'm gonna get my phone now and compute as well. DPU. No one would like to hazard a guess? Okay, so let's think this through. So in the first one, we will count the number of defects. How many defects did we have in the first one? If you can put in the chat box, how many defects did we have? Remember, I'm asking for the defects, not the defectives. How many defects did we have in the first one? We have actually 4. Okay, we have 4 because in the first there were 2 forms that were defects were encountered. The first one has 3 and the second one had 1. So 3 plus 1, we had 4 defects. How many units did we have? We have 50 units or 50 forms. So the DPU here will be 4 divided by 50. Okay, so let's see if you got it right. Oh, sorry, this one is wrong. This is supposed to be defects per unit, so it's 4 over 50, it's 8%, correct? And the other one, the DPMO, by the way, so this is wrong, okay? Let me just correct this one. This one should be 4. Okay, so 4 divided by 50, that's 8%. And the DPMO is, what's the DPMO? Let's see. I haven't computed that. 4 divided by, you have 50 forms and 30 fields divided by, haven't bit. Yeah, 4 divided by 1.5. Yep, times 1 million. And the answer is 2,666. So correct. Thank you, Karen, for your answer. Okay, let's have another example. So let's say an HR form has 20 fields and Paula went to 2,000 HR forms and found 3 defective forms. So she found 3 defective forms. One form has 5 defects, okay, which is about wrong name, age, civil status, address, and blood type. Another form had 2 defects, wrong SSS number and a missing contact number. And still another form had 1 defect, missing field health number. What is the DPU? Okay, how? If you can compute and add in the chat box. So the DPU is 0.4%, correct? Okay, 0.4%. And the DPMO, can you compute for the DPMO? The DPMO will be, so let's see, it's already here. Okay, so the DPU will be 8 over 2,000. Okay, where did the 8 come from? It's 5 plus 2 plus 1 divided by the 2,000 is 0.4%. The DPMO is 8 divided by 2,000 times 20 times 1 million. It's 200, the DPMO. So correct. Congratulations, Karen. You got it right. Where did the 20 come from? Ito sa baba. This 20 here comes from, okay, let me just check one. The 20 here is coming from the opportunities. So you had 20 ways that a form can have an error. So how did we again arrive at the DPMO? We just count the number of defects. The 8 here is the count of number of defects, which is 5 plus 2 plus 1. These are the total defects that was encountered, divided by 2,000. Where did this 2,000 come from? This is the total number of units that we have. Okay, and each unit has 20 opportunities. Okay, and then multiply to 1 million, and the answer is 200 DPMO. Okay, so that's how you compute for the process capability if your process is dealing with discrete data. Now we go to what if your process now is dealing with continuous data. You're dealing with continuous data, you are describing your process in terms of the CPK and the sigma level. Okay, let's continue. Okay, I will now flash back again an example I've given during the introduction session. So imagine we are dealing with chewing gums and we are measuring the weight of the chewing gums. And like a normal process, every process has variation. So it's not always that we get the same weight of a chewing gum. It could be the target is 3.2, but sometimes we can get 3.1, 3.0, and so on and so forth. Because variability is normal for any process. Okay, so we have this weight of stick gums, and then we try to map it using the histogram. It's this. We found out that the weight of the stick gums is distributed in some sort of this manner. We have a high frequency somewhere near 3.1, and as we move to the left or to the right, the frequency goes down. Okay, and then because this is continuous data, if we have fine instrument that can measure down to maybe 10 or 11 digits of the weight, slowly the distribution will assume what we call as a normal distribution, or a curve that looks like this. And then in the example that was previously given, we have specification limits from for our process. We don't want to go below 3, and we don't want to go below 3.4 because that will be costly for the company. Okay, and anything that falls in the limits are considered as defects. So when you produce a process, there's a possibility that the output could be within the specification limit, or there is a possibility that the output that you have will fall outside the specification limit, and anything that falls out is considered a defect. So now your process would have a mean, okay, there is an average, and there is a standard deviation, or how scattered your data is. Any process would have a mean and a standard deviation. If you have a poor process, okay, your process is a bit scattered, it's a high standard deviation, you have higher opportunities of your process getting out of the specification limit. You have a higher probability of defects. But if your process is so good, okay, it's very, very consistent, the probability of your process of falling out is very, very small, or just a low probability of defects. So in this case, if you have a low probability of defects, you will have a good process capability. It's very good. But if you have a high probability of defects, your process is poor. Okay, and there's a way to measure this probability of defects, and this is what we use as the CPK. So the CPK talks about the process performance. Okay, so it tells you it's a measure of how your process is performing according to a specification limit. Okay, but there's another topic that is also related to the process performance. The CPK is also called the CP. This is what we call now the process potential. The potential of your process, or the best way possible that your process can form. Okay, and we will discuss how to compute for the CPK. So the CPK is just a measure. Okay, it's just a measure of how far you are, how far is your average from the nearest specification limit. So it could be that your process is going to have more defects on this side, or it could have more defects on this side. Okay, but if your process is operating on the center, okay, there's an equal probability to have defects on other limits. Let's have some scenarios here, comparing what we call CPK. Okay, how to compare process potential with the process performance. In the first example here, okay, so let's take for now that we have computed the CPK and the CP. In this case, the CPK and the CP are equal because your process is centered. Okay, your process falls within this one. In the second example, notice that your CP is still the same, okay, because CP talks about potential. But your CPK here is now low, it's lower, it's 1. The reason for this is, although you have, you still have the same distribution, okay, but this time your average is nearer to this upper specification limit, which means that you have a higher probability of having defects exceeding the limit. Okay, and that's why your CPK now is lower than your CP. And further here, in the third example, you still have the same distribution, but now the average, or your mean, is much closer to the specification limit, which means that you now have a much higher probability of defects compared to B. So in this case, your CPK is much lower. So the lower the CPK, okay, the trend now is the lower the CPK, the higher is the probability of your defects. And we will compute now how to, we will go now how to compute for the CPK. So you just remember that a process capability can have two possible problems, okay, in terms of the defects. One is that your process is not on target, okay? For example, when you have an off-target process, you have very consistent, let's say, you have very consistent performance, but you are not hitting the target. So a good analogy is here, in this case, you're trying to shoot for the bullseye. You're very consistent, but you are off target. Okay, so that's the analogy of this example here. Another one is you could be that you have a very poor variation, or your process is very consistent, just like this. You are aiming for the center, however, your process is quite scattered. That will be mimicking this kind of example. And the goal actually is to center your process. Okay, it's to center your process, but at the same time to reduce the variation. Okay, that's always the goal of a Six Sigma project dealing with continuous data. To hit the target and to reduce the variation. And that value can be measured through the CPK. Now let's go to how to get the CPK. So the CPK is just quite simple to compute. Okay, so I'll just give you the theory first, and then we will do the application later. The first one is you need to determine the specification limits. Okay, what are the limits that are required by your customer? Okay, and the next one is you just get the mean of your data. The mean is quite easy to get. It's just the average. Okay? If you're given the data, you can just compute it using Excel. The next one is you get the standard deviation. The standard deviation is the measure of how scattered your data is. Okay? And next, you just determine which one is the nearer specification limit. So it depends on your data. You look at the mean, you check which one is it near, which specification limit is it nearer to. And then you can now calculate for the formula of the CPK. You remember we're computing for the CPK. The CPK is you just get the nearer specification limit. You subtract the mean or the average of your data. This is the absolute value, and you divide it by 3 times the standard deviation. Okay, just remember this formula. This can be a bit intimidating, but once you get an example, that will be quite easy to compute. Okay, so just remember this formula. CPK is equal to the absolute value of the nearer specification limit minus the average of your data divided by 3 times the standard deviation. Okay, so I know this might be nosebleed right now, but hopefully this example will make it clear for you, because the human brain can easily associate it with a specific example. And let's have a specific example now. So imagine Roger working in a chewing gum company. Okay, can I ask someone to, just to keep you engaged, can I ask someone to read this one? Any volunteer? Maybe I'll ask someone to read. Let me see the participants. Who can I? Any volunteer? Can you put in the chat box? Can I ask maybe Karen? Karen, can you read? Can you read the one on the chart, please? Go ahead.
Roger works in a chewing gum process plant. He is assigned to a line that produces stick gums. The target weight for the stick gum is 3.2 grams. The lower specification limit is 3.0 grams, and the upper specification limit is 3.4 grams. Roger collected a sample of 100 gums spread across his 8-hour shift. The average weight is 3.25 grams, and the standard deviation is 0.05. What is his process capability?
Okay, thank you, Karen. Okay, so now we have an example here where Roger is working in a chewing gum company. Okay, and he has a target weight of 3.2 grams. There is a lower specification limit of 3 grams. Why do we have a lower specification limit? Can you answer in the chat box? Why do we have a lower specification limit? If you can recall what we discussed. I'm going to read your response in the chat box. So why do we have a lower specification limit? Anyone? Yes, in this same process. Why do we have a lower specification limit in this chewing gum process? Why do we require that we should not exceed below 3 grams? Okay, our target is 3.2. Okay, very good. So I got a response that I've been waiting for. So thank you, Karen. Because there are federal or national government regulations. Okay, because if you're selling a chewing gum and you're putting in the pack that it's 3.2, and suddenly they, the regulator randomly selects your product and weighs it, and it's below 3 grams, they can sue you because you are misleading your consumers. You are stating in your pack that you're selling 3.2 when in fact you are shortchanging your customer. Okay, so they would allow maybe some variation in your pack because variation is normal, but if it's consistent, then that can be considered as cheating. So that's why in your process, you will have a target limit that you should not go below 3. The next question is, why do you have an upper specification limit of 3.4 grams? Okay, very good. You don't want to exceed because if you have more than, you are giving more, you're charging your customer 3.2, but you're giving them more than 3.4, then it's lugi. Okay, you will lose profit. Okay, good. So you now understand the concept of this specification limit. So Roger has collected a sample of 100 grams spread across his 8-hour shift, and the average is 3.25 grams. So now in this problem, it's easy for everyone because the weight is now given. Okay, and the standard deviation has already been computed. So the question now is, which one is the nearer specification limit? Is it the 3.0 or the 3.4? You answer in the chat box. Which is the nearer specification limit to 3.5? Is it 3.4 or 3.0? Anyone? The answer here is 3.4. Yes, correct, Hannah. Because 3.25 grams is much nearer to 3.4 compared to 3.0. Because the middle is actually 3.2. So 3.5 is nearer to the 3.4. What is the interpretation of this one? This means the interpretation of this one is you are more likely to have a defect of being overweight rather than underweight. That is just the interpretation of when we mean by which one is the nearer specification limit. Okay? So in this case, the mean is more shifted towards the up, which means that your process is more likely to produce errors of exceeding the 3.4. So now the question is, what is the process capability? Can you compute? Okay, or maybe you can compute on your own. Let's flash it. You should be getting an answer of a CPK of 1. Okay, so how do we arrive at CPK of 1? The nearest specification limit is 3.4. So 3.4 minus 3.25 divided by the 3 times the standard deviation. And the answer is 1. So your CPK here is 1. So now you'll be asking, okay, now I know that I know that my process has a CPK of 1. What now? Okay. So 1 is actually, once you now get the CPK, this is where the magic happens, because a CPK can be converted into a DPMO, a sigma level. Okay. Actually, there is a table that can relate to CPK to DPMO. That will not be covered in Yellow Belt. There is a mathematical formula for that one, but for now, you can just look at a table to convert a CPK to a DPMO. So now, Because if you have a continuous data, in continuous data, you can get for its CPK. And once you have the CPK, there is a table where you can reflect a CPK to a DPMO. So in the example that we have, 1 is actually in the table corresponds to a 66,000 DPMO, or the yield will be about 93%. Okay, so there is again, there is a table that you can use as a reference once you have the CPK to convert into DPMO or to the yield. So in the process that we had earlier on the chewing gum, we can say that 7% of the time, our product would be defective. Okay, so let's say of 100 chewing gums, 7 might be defective. Okay, that is the interpretation of the CPK. CPK, you can get DPMO and yield. And this is where also the magic happens. The CPK can also be converted into a sigma level, okay, by multiplying it by 3. So CPK multiplied by 3, you can get the sigma level of your process. So you can now say that in the process that we had, Roger's process is actually operating at 3 sigma. Okay? But if Roger's process had a CPK of 2, his process would have been operating at 6 sigma. And that's where the description now of the 6 sigma comes in. A process that is 6 sigma has a CPK of 2, has a DPMO of 3.4 defects per million opportunities, and it's operating at 99.9997%. Actually, it's 999.96%. Okay, so this chart only shows you that a CPK can be converted into a DPMO. So now compare apples to apples. If you have a discrete data, remember, if you have a discrete data, you can immediately get for a DPMO. If you have a continuous data, you can get first the CPK and then get its DPMO. So actually, you can now compare apples to apples. You might have a process that deals with continuous data, and you have a process that operates at discrete data. Eventually, you can still compare its DPMO. So you can say whether one process is better than another process. Okay, so I hope somehow that lifts the mystery behind the concept of sigma. Okay, something is wrong with my chart. Okay, let's move on. So in real life terms, okay, if you have a 1% defect, okay, 1% defect is actually 3.8 sigma. Here are some examples in real life. If your task is to provide safe drinking water, if you have 1% defect, you will have 450 minutes of unsafe water each month. But if you have, if you're operating at 6 sigma, you will have only 1 minute of unsafe water every 7 months. But this one is my most favorite part when I try to compare 6 sigma versus 99%. If your task is to provide electrical service, if you're operating at 99% or 3.8 sigma, you will have 7 hours without electricity each month. But if you're operating at 99.9997% or 6 sigma, you will only have 1 hour without electricity every 34 years. So sigma level can actually be associated with defects. So we're giving here 2 examples. If your process is operating only at 2 sigma, your process is a bit scattered. You're only able to fit in 2 sigma deviations of the process within the limit of your customer. Okay? And your CPK here will be lower. But if your CPK is, let's say, 3, that's equivalent to 6 sigma. Your process is very, very consistent. Okay, it's very, very consistent. You're able to fit in at least 6 sigma deviations within the specification limit of your customer. Okay, that the probability of a defect is very, very low. Okay, so that's how we visualize what a 2 sigma process versus a 6 sigma process would operate using the specification limit. And as we said, you can get the sigma level if you know the CPK. Okay. So that's it. That's how the sigma level is related to the defects. So we've covered how to compute for the CPK, and from CPK you can get the sigma level. Sigma level you can also get the DPMO, the defects. I now leave this to you as a problem that you can do on your own. Okay, let me just read. Maybe I'll ask someone to read. Maybe Winby, can you read the exercise?
Yes, sir.
Yep, can you just read the
A
exercise?
terrain,
Go ahead.
okay po. A train department wants to improve customer satisfaction by ensuring on-time arrival of trains. To start their analysis, the team would like to determine the current process capability of travel time from station 1 to station 2. The past 30 train duration data has been collected. The said process has an upper specification limit of 220 seconds and lower specification limit of 160 seconds. The team collected the following data to start their process capability analysis.
Okay, thank you, Winby. So in this example, we're talking about the train travel. These are just hypothetical specification limits. So maybe there is an upper specification limit because we don't want our passengers to be late. Okay, because if you go beyond 220 seconds, your passengers might complain already. They'll be late for their appointment. But at the same time, we want to also consider the safety of the passengers. So we don't want a too much of a fast train. So we also have a lower specification limit of 160 seconds. So those were the specification limits come from. And the data is given here. Okay. So the challenge now, the added difficulty here compared to the previous example, compared to the chewing gum example, is in this situation, you will be the one to determine the average. Okay? So you will have to compute for the average, and you will have to compute for the standard deviation. But once you compute the average and you get the standard deviation, you will determine the nearest specification limit. And from that specification limit, you can compute for the CPK. And once you get the CPK, you can get the DPMO and the sigma level. So that's very much how you would attack this problem. So I leave that to you to solve, and you can maybe I'll give you a week to answer. You can put that in the post in Facebook. But hopefully, with what I've covered, you should be able to compute for the process capability. Okay. Okay, so with that, let me end the session, stopping the sharing, and we can proceed to the question and answer.